Thank you, madam. Thank you for the kind introduction. So, is my screen visible?
Yes, yes.
Madam, is it moving?
Yes, yes.
Oh,
Please
great.
carry on.
Thank you so much, ma'am. Thank you so much. Thank you for giving me this opportunity. So in this presentation, I am presenting the experimental works which we have been doing in CDAC Pune. We have established a quantum technology lab, and there we are working under two projects from MIT. One is terrestrial QKD for financial applications, and the other one is the uh, quantum communication or quantum key distribution in an aerial platform. And we are looking at drones. So we will be generating, this entangled numbers, entangled or a quantum signal. I mean, we know that there are, so in the presentation also, I will be discussing on how we generate single photons, and establishing a communication between these two platforms, which should be mobile and it should be agile. Now, in this journey, there were several spin-outs, interesting spin-outs, which I will discuss in this presentation. So, considering we are all celebrating quantum this year, which is 2025, and it is because of the completion of 100 years of Heisenberg's paper on quantum matrix mechanics. And so I will start this with entanglement. Now, this is a property which enables you to demonstrate several, marvels, should I say, or should I say, gives you higher, more advantage in some aspect from the classical world. Not all, but some. But that is very much that is interesting and has economic associated with it, and that is the reason we have now National Quantum Mission. We can understand its importance. So now let's start discussing the entanglement. We'll start with the story. So it all started in 1905 when Einstein was, credited with the photon and as a discrete carrier of energy. And that time Heisenberg and Bohr started talking about quantum mechanics. During 1925, and that is the reason we are celebrating 2025 anniversary. So the quantum mechanics talks about non-realism, non-locality, which made him uncomfortable. And thereafter, Einstein, Podolsky, and Rosen, they gave a fundamental paradox. The title says, "Can quantum mechanical description of reality be considered complete?" So after that, Schrödinger in 1935, he published a paper on the consequence of wave function collapse, and he was a person who termed the word entanglement, right? And ironically, both these works, which were actually questioning the existence of entanglement of quantum mechanics, they became the foundations of this technology. Then, so now you have the theory. Then Bell was fascinated by Einstein paper, and then he was looking into a hidden variable. He was seeing if the hidden variable is compatible with quantum mechanics, and he came out with an inequality. Now this is where things get interesting. Now he proposed the inequality, which will be obeyed in the classical physics classical world, and he found that the quantum mechanics actually violates it. Then it was experimentally verified. So then it was difficult to verify it experimentally, and Clauser came into picture, and he was astrophysicist. Okay, and he then formulated the inequalities in a manner that it can be experimentally tested. The reason I'm building the story is because we have done this inequality testing in our lab. So when we are proving, or when we are doing this tests which verifies which violates the inequality, then we are actually in the quantum domain. It's a non-local interactions which we'll be referring to. And so the theory, then you have a proof, then you experimentally test the proof, and then you have the experimentations which was done by Zeilinger. So, and you can see the political importance of this technology as well. So now coming to what does it actually mean? What does an entangled state actually mean? Now, I had the opportunity to listen some part to the previous speaker, and it looks to me that the entanglement is clear. So we will just maybe briefly. So by entanglement, we say that if one particle, say, is with me in Pune and the other particle is sent in Bhubaneswar, then if particle 1 is measured and found to be, say, for example, as you can see here, horizontally polarized, the other one will also be horizontally polarized. So there exists strong correlations. At the same time, whether on measurement I will be getting a horizontal or a vertical, that is that appears to be absolutely random by the theory. And whenever we are doing the theory we are taking it to on experimental test bench, we have to understand a lot of biasness and classical noises. So how do we take care of that? And we generate a high throughput and high quality entangled state is a very active area, and we do have products also in market. And also we know that the entangled state cannot be written as a separable state, something which cannot be written as separable state. So with that, we move forward. And so here is the introduction, which I think I just mentioned. Now, these are the 4 Bell states. H is horizontal, vertical, and I have already discussed. So we will move forward. Okay. So we would like to now verify whether this is an entangled state or not. Okay, so and if it, or is it a separable state? If it is not separable state, then it is an entangled state. So we do some maths, we expand the state, and then we find that we reach to some conditions where we find that the entangled state cannot be actually written as a separable state. So it has its existence, and its uniqueness lies when both are together and they are highly correlated. Now, this is the experimental test bed. So you can see the laser here, and there is a lot of filtering, purification which happens before we inject the pump beam to the BBO crystal. You can see this is the nonlinear crystal. We will discuss about this experiment, about the generation of the quantum source, single photon sources in the next section. But so far, let us see that whether this is actually possible or not. So you have a milliwatt, a pump beam, it's in milliwatt, but the entangled photons, which is coming out with a probability 1 in billion, which is coming out in a probability 1 in billion. So those have to be, you can see the blue line, which is the pump beam again. So there is a filtering again of the pump and the daughter photons. These are the entangled photons. So you can see that we have now separated them into 2 different optical paths. And then we again filter them out, and we capture them using these 4 detectors. We do have to, understand whether it is a horizontal basis states or a diagonal basis states. So for all that, no, I mean, more and more optics gets added here, because we will be expanding this setup for a BBM92. We'll be doing a a QKD protocol out of the entangled states, but primarily it comprises of, this is a basic setup. Okay. So, so then we move forward, and these are the beam splitters, polarization beam splitters, which will pass the horizontal and will reflect the vertical. So here is one demo I would like to show, though I'll be discussing about the process of generation later. We have to do a validation of this generation of daughter photons or entangled photons, and that calls for a unique condition. But when I am actually reaching that particular condition, which is a phase matching condition, you will see a ring. And whenever I am trying to deviate from that phase matching condition, the ring will disappear. So let me just show you that demo. So this is the experimental setup, and what you can see here is the EMCCD camera. Right now we'll be showing you the picture or the visual confirmation of the generated photons. So you can see the ring here, the intersection points of these two rings on the lower side. We will be focusing our optics and collecting the intersection point. So this is one of the photon pair, and the other particle will be collected from the other side of the pair. You will also see that as and when we are distorting the phase matching condition, the ring will disappear. So now I think we are trying to show the other side of the ring. Okay, these are again the intersection points which we will be collecting. We will be focusing our optics so that we collect the photons coming out through these intersection points. Now, when the phase matching condition, Umang is changing the phase matching condition, you will see the ring disappear. Yeah, it has disappeared. And again, we will bring it back by changing the optics. Yeah, so this is a confirmation, visual confirmation that entanglement is generated. And thereafter, we have to do a lot of alignment to capture the intersection points. Thank you. And thanks to my team. Then we move forward. Now, we had discussed about the CHSH inequality, the closures inequality. Now, this involves a particular combination of expectations value. So forgive me, I should be adding because these are all polarization degrees. It's a 0 degree, it is a 22.5 degree polarization angle, 45 degree. So for a particular set of the expectation values, and each and every expectation value has to be calculated with respect to certain orientation of the polarizers. C stands for the coincidence counts. As per the classical limit, it should be less than or equal to 2. But the moment you are exceeding 2 till 2 root 2, which is 2.8, you are in the quantum domain. So this is a result we have got, which is 2.67. So we are in the quantum domain, and we have and the classical there's a violation of the classical inequality. Okay, so now we'll talk about. So this is a ring, if you remember. So am I audible to everybody? I mean, I hope I'm.
Yes,
you're in sync with me.
Yes,
okay. Okay, thank you. So this is a ring which I was showing, the upper end of the ring and the lower end of the ring. Okay, so these are we'll be capturing these two intersection points. So when we say HV plus VH, it will be an H and a V here, or a H or a V here. Okay, so what we detect, or after it, because entanglement is nothing, it is also a special superposition case. So if I say HV plus VH, then it is H here, then I should get a V here. And if it is a V here, I should get an H here. Then we have also ran the data with the tomographic results, and we have got a very high fidelity. We have got very high polarization visibility. It took us a lot of time and improvisation to achieve this stage. And you can see how we are taking the coincidence counts through a counter. Now, after having generated the entangled state, we wanted to do some application out of it. So one quick application was the QRNG. So how did we build the QRNG? So we know that, we are generating, so we will be detecting either HH or VV, and the randomness lies in the wave function collapse of either being HH or being VV. So I assigned a number. Say if I'm getting HH, then I will say 0. If I'm getting VV, then I'll say 1. So the way the wave function collapses, if I'm getting an HH, I will say 0, VV 1, 0, 1. So like that, I go on increasing the binary sequence. So this is how QRNGs are created. And the quantum entropy here is on wave function collapse. It is called, it is entanglement based. Earlier, in my career, I have generated QRNGs using path superposition, then temporal time of arrival. And when I was working in a company, I have improvised the system and I could generate till 100 Mbps per second. Now, of course, I mean, if you can scan, I hope if you scan, you will get access to some of the random numbers, and the tank gets refreshed after every minute. And this is one of the test suite which we had, applied to our data, and the result looks like it was behaving as per our expectation. But again, it is a hardware device. Hardware means loopholes. Hardware means non-ideal, and all that, and maximum interference from the classical, be it any type of noise, phase noise, electrical noise, electronic noise, as well as data storage, data fetching. Many sources of errors are there, and that has to be identified and filtered. So this is one application. Now, once we have generated the QRNG, we did a secure communication between two offices in our building. So we have our internal network. We took so this is a path superposition based QRNG. As you can see, you have a laser attenuated, so to almost a single photon level. And whenever either of the detectors are clicked, that corresponds to one of the binary logic. So this is another way of creating a QRNG, which we have done, and we have validated the results also. And this is a quick way. So what we did, we seeded the PQC, post-quantum cryptography, with the QRNG data and established a secure communication, or a secure, I don't want to give more names to it, but just let me keep it simple and say secure quantum secure communication using a QRNG seeded PQC. And we also did most of the hardware implementations in-house. And this is the test result of the random numbers generated using path superposition. So any questions here? Because there will be 3 sections. The next section will talk about a photonic quantum computer for education purposes, and the last section will be on QKD. So any questions on entanglement here, on how we have generated or what is the application? Okay. If not, then I will continue to the next presentation, which is on virtual plane. Sorry, it is taking the qubit from a virtual plane to a physical plane. So we know what a bit is, right? I mean, we are almost at the end of the school, so I hope we understand what a qubit is. So can somebody please confirm, because I'm the idea about qubit, gates, circuit, is it clear, or should I get into it?
Ma'am, I think it is clear to everybody.
It is clear. Great. So the block sphere and all, we know the pure state and mixed state. That's great. So now if you want to realize a qubit, we will take, for example, the path superposition state, which we had taken earlier. We have a single photon. After a beam splitter, it is a 0 and it's a reflected or transmitted. So I'm assigning a binary value to the paths. So this is called coding. Okay. So if I'm having, so this is called coding. At the same time, you will see that this behaves like a Hadamard gate, where you have an input photon. And after the Hadamard gate, 0, you have input, you have a Hadamard gate, and then you have half the probability. So it is a 50-50 beam splitter. You have half the probability of getting it detected in either a logic 0 path or a logic 1 path. So this is an optical gadget for photonic quantum computing. So this is a spin out basically of our project, and so we don't get too much into it, but let us see how it can be also useful in the present national ecosystem where education is a priority. So you can also give me your feedback, and we can improvise on the setup. So coming back, we know a NOT gate. This is a truth table, so it inverts the logic. And physically, a NOT gate is made by a transistor. You can see the breadboard implementation. Now you have a quantum NOT gate. So a quantum NOT gate will change the binary logic state. So if the binary logic is encoded in polarization, and let me say the horizontally polarized light is get 0. So psi input after a half wave plate, which is again another optical gadget which changes the polarization angle to twice the value. So if it is about, say, horizontal, and I'm giving it a 45-degree orientation, so it takes it to 90 degree. So a horizontal becomes a vertically polarized light. So it flips the state. Okay, so this is how it is interesting. So I hope with all the we can modify the any input state with a combination of some of the photo optical gadgets. So this is one such thing. Now coming to the generation part, generation of a non-classical light. So in classical field, so this is another type 1. Earlier we had seen type 2, which was the overlap of two circles, the intersection points giving me entangled states. And this is a type 1 generation of correlated daughter photons. So in classical field, in a classical field, we mean an electromagnetic wave which will be perfectly described by the Maxwell's equation, right? No? And for such a field, the second, the correlation between the intensities, the transmitted intensity and the reflected intensity, is given by the second order correlation function or second order temporal coherence, or let me say second order coherence. And it is a function of time delay between the intensity measurements. Time delay between the intensity measurements. And we are interested in one such case where where we do simultaneous intensity measurements. Okay, simultaneous intensity, so tau is equals to 0. So this is my coincidences. Clear? And the reason why I am calling it second order is because it is the intensity. Otherwise, first order correlation function is between the fields. So if you have a 50-50 beam splitter, where transmitted and reflected light will be half of the intensity of incident. So we will come across such an equation which is shown in 2. And using Cauchy-Schwarz inequality, we find that any classical light will have value greater than 1 for any of the classical fields. Okay. But if I'm going to the quantum field, now the quantum field is not fully described by Maxwell because here the electric fields are treated as quantum mechanical operators, and rather than taking the classical waves. So when a single photon is at the input, then the second order coherence, it will be 0 if it is a single photon, which violates the classical inequality. So here again, we are using the non-classical light to to do some things in the classical world, which is which challenges the notion of many results, I would say, in a very broad level. So fine. The conclusion is, whenever we are generating, whenever the generated single photon states are there. Now, how we generate it is a different thing, but the single photons will have a second order coherence function, which is less than 1. So it is a check. So if I make a product and I claim that it is a single photon state, it is using single photons, then this test, other tests are also there, I would say, but a second order coherence is a good test to validate that the device is, I would say the device is actually working in the quantum. Otherwise, through bare eyes or any other things, it is very difficult to convince people that you are actually working in this technology and you're generating the single photon states. Now so single photon is a must. Single photon equal to 0 shows anti-bunching property, which means that photons are not traveling together. And that is where the anti-correlations of photon detection at the two detectors happens. So that's an interesting case. Now, how do we generate? Most of the time we are generating using spontaneous parametric down conversion, where here the input beam is referred to as pump at an angular frequency omega p, as you can see. Please refer to these two equations. And the two outputs are referred to as signal and idler. So energy conservation. So the first equation here, I'm not able to. The first equation here is based on energy conservation. And the second equation is the momentum conservation. It is equivalent to classical phase matching condition. Okay. So these two conditions, once it is satisfied, then I'm getting these cones. So earlier you had seen these cones in the diagram. Now, and these are the intersection points. Now you see why I was talking about the intersection points. So, so this is again, I think right now beyond the scope of on how it is generated, because you need to understand the device properties, the quantum optics, the physics behind the generation using a nonlinear crystal. There are other ways also. We are using type 2, but you can also use combination of type 1 in a certain orientation. Okay, so single photon importance, and then we have generation. Now, a quick look at the gadgets. So this is a polarization beam splitter. Horizontal will pass and vertical will be reflected. So you can see, and if you use them in certain fashions, it provides you method to validate many of the measurement based upon the application, right? I will not go further. I think this is evident how, see, this is a trick. So you can make many tricks out of this combination or playing with this polarization beam splitter. That is the reason I put it out as a single slide. It's a very important optical gadget, not only from making this technology, but also from any sort of adversarial attack you would want to build to hack a quantum communication system based on maybe polarization encoded, so free space. Now, our purpose in this slot of the presentation is on computing. So let's talk about the gates. So these are some of the basic gates. In our setup, we have tested NOT gate, Hadamard gate, and identity gate. It's in the beginning, and we are also figuring out, how to use combinations of wave plates and work other gates out as well. Now, you can see here, you have a circuit composer. This is something which can be built by any student. So one such intern had come to us, and we designed this circuit, which is from an open source, which is web-based source. Then the thing is that whenever I am dragging and dropping the gates in this circuit builder, corresponding information is being sent from the simulator to the backend, which is a quantum processor. I would say a quantum processor. It's a very I would say first level or crude method. We have generated a heralded setup where a single photon generates signal and idler. One of the photon is used as a gating medium, or it gives a confirmation that the second photon is also generated and confirms the existence of the other single photon. Okay, and that is what we use in to apply these gates and get the corresponding outputs. So if it is a Hadamard gate, maybe I would like to put a polarizer oriented towards a particular angle. If it is a NOT gate, I will orient it towards another angle. So that is an automation which comes in. So this entire system, I would say, programmable because I'm able to program the qubits. At the moment, it is 4 to 5 gates, which we are looking at if we can expand. So this is, and we are not considering 2 qubit gates. We are, it's more from an education perspective. So it's a single qubit system only. The photons are generated using SPDC. I told you, okay, so logic 0 and logic 1, you will see the count. So I will give a demo here now on this setup. You will see the circuit builder. You will see the Quasum code. You will see simulator, which will give you, ideal output, and you will see the experimental results also. So am I still audible? I mean, I hope you have not lost me and I have not lost you.
Yes, ma'am, you are audible.
Okay, thank you. So you can see the setup here. Here is the simulation result. Here is the real-time hardware result. So if I'm dragging, say, identity, if I'm dragging identity and it is a logic 0 state, then obviously my output should also be 0. So you will see in the computational basis state, 0 will have the highest value, 100%, and 1 will be 0. But if you look at the real-time results, you will see logic 0 will have highest, but logic 1 will also have some subsidiary counts. Now, why is it? Because when you were seeing the experimental setup, the detectors are only 10% efficient. There are clicks when light is not there, which is called dark counts. Now, the photons, the polarization beam splitters are not 100%. They are not ideal. Okay. So a lot of things contribute to noises. Now, these are the noises primarily in a optical setup using linear optics. But as and when the technology is changing from optics to superconducting to ion trap, the sources of noise will change. The noise amount will change. So mitigation changes, noise mitigation, noise sources of errors will change. So let us quickly play this. So you can see this is identity gate. As I told you, it has the highest measurement completed. Real-time results, 6,000 counts in logic 0 and logic 1 with 300 counts. Now we will apply another, and it is totally at random. I mean, it was a live workshop. So now it is a NOT gate. Quasum code is there. Logic 0 input, so logic 1 is highest. You can see in the simulation. Now real-time results, measurement is completed. So you will see the maximum counts in logic 1 and noise in logic 0. Now we put Hadamard in simulation. You will quickly see the simulation results, 100% and 50% at both the logical states. Now let us wait for measurement. So you will see 5,800 and 5,600 counts in both the detectors. So any question here? So again, I will be going next. I will be moving to QKD. So before that, if you have any question, I will be happy to answer. Did you find this interesting or any feedback? Yeah.
Ma'am, what is this software you are using? What is this called?
No, we are not using this software. Is built by one of the students. So this page is created by them. And then whenever a quasum code is generated, we kind of take the input from the circuit, which is there, say, in the first floor. And my lab is in the third floor. It is actually in the third floor. So the instruction goes via a network. And then we have, I would say, a compute and a communication system, which can be a laptop to begin with also. And there the information is processed and then the corresponding control operations are given to the quantum hardware. Then the measurement is taken. Measurement is again similarly goes from the detectors. It goes back and is then published in the circuit composer page. So this is the entire. See, when you're looking at a quantum computer, there are different levels. It starts off with the circuit composer. Then you have the quasum code. Then there are compilers, then transpilers. Then you have the instruction set architecture. The instruction set architecture actually gives the commands or the control operations to the quantum hardware. Based on the nature of hardware, this changes. For superconducting, it is different because you have cryos and you have microwave components. For optics, it is different. So the software which we have built is actually based on the design of the hardware and on the because that is more of a design, how the front end is talking with the back end and what the back end. This is the experimental setup, but when you're actually operating many gates, the setup also gets modified. It will become more complex. A lot of filtration, a lot of automation happens. And then after that, the laptop or the compute system at the third floor will again publish the result via the network to the ground floor located web page. And before everything, we do a checking whether the second order coherence is less than 0 or is less than 1 or not. Could I answer your question?
Yes, ma'am.
Hello, ma'am.
Hello?
I was asking, is this a 1 qubit system?
Yeah, it is a 1 qubit system. But when you do 1 qubit, you have to understand there is a lot of measurements you take. Okay, so I didn't get it. Please, can you repeat?
If it is a 1 qubit system, so how many gates can we use at one time?
Well, it again depends upon the complexity. Right now, we are right at the moment, it is very basic and few of them. But as and when we go on, we can increase the circuit width, circuit depth also. But that is again a different, different set of work. There is no limit as such. It depends upon the algorithm you are executing, how many single qubit gates will be applied. At the moment, I cannot say that, this is the capacity, because it again, the capacity and the resources are very, very connected. Okay, so for having large number of qubits, there will be more infrastructure, more space required, more automation, controllability. That will be an add-on. At the moment, there are just few gates for education purpose only. Basic poly gate. So we are working on the phase gate. So we would want to restrict ourselves to few gates. Did I answer your question?
Like I was asking, like how much depth where we can have for circuit, like how many gates can we use at one time?
Oh, right now it is just one gate at a time. And you see, if you are applying 2 to 3 gates, I would not say that it is not possible. It is quite possible, because again, it is a matter of finding out the right orientation by multiplying the gates together, and then finding out what is the optimal orientation required in the hardware plane, and it can be given. So maybe, we are actually looking at combining 2 to 3 gates and finding out the required orientation or required controllability features which we have to give it to the hardware to get the output. For example, Hadamard or NOT gate combining, playing with some basic gates, combining maybe 2 gates. So if I apply or combine 2 to 3 gates together, it will increase the complexity. And it is again a lot of R&Ds involved.
Yes, ma'am. Thank you, ma'am.
Okay. So now we will move to QKD. So QKD stands for Quantum Key Distribution. Now the name is little deceiving, because we are not distributing the keys. We are actually generating spontaneously and spatially separated parties, partially, I would say, correlated binary sequence. So theoretically it is perfect, but when we are doing experimentally, it is partially correlated, and thereafter we do a lot of steps, classical steps, to arrive at a perfectly correlated key pair. So it is a symmetric key cryptography. In symmetric key cryptography, you need keys. You need symmetric keys, which means at Alice and Bob, they will be same keys. And QKD is a physical solution, in a realistic solution, because there is no other solution to send your data securely from one place to another. You do not have any control on the key distribution. Because in the classical world, we are using public key infrastructure where you generate the keys and you send the key to the other party using some mathematical problem, which can be broken today by a quantum computer. So that is the reason people are moving to post-quantum cryptography. That is a problem statement which cannot be broken by a quantum computer or is assumed to be secure. And QKD is a hardware. It is not a hardware implementation of PQC. No, it is a different method of generating correlated keys at two different locations using quantum mechanics. And also the security is guaranteed by the laws of quantum mechanics. For example, no hiding, no cloning, all these theorems, uncertainty principle. So whatever I spoke to you right now is the QKD protocol. We know about BB84, right? So there are many such protocols. BB84 based on single photon is the best, but still now there is no standardized QKD protocol, and scientists are actively working on coming out with some breakthrough protocols, or coming out, or at least standardizing one such QKD protocol so that it can be adopted. Now, let us look at the architecture. So, in a QKD protocol, following some quantum algorithm, okay, now algorithm means a sequence. For me right now, it is a sequence. It is not the quantum algorithm which comes under computing area, okay? So, some sequence of steps is there. For example, BB84 and all. It involves data transfer. So, this is all what is quantum. Rest, everything which you are seeing is classical. So in the quantum data transfer, following a protocol, we generate correlated photon pairs, correlated binary string, partially correlated binary string. And after that, we do sifting, which is basis selection, if you have different bases involved. In some protocols, the sifting parameter is only one. And then you have error estimation. You find out whether the error is more than the threshold, which can be, each and every protocol, you will find an error threshold based on a deep analysis on the security. Okay, that threshold should not be crossed. If it is more, then it is aborted. If it is less, then we go on to correcting that error. Again, error correction is also probabilistic. It is not 100%. Okay, so it is so each and every blue box you are seeing is a active area of research. So sifting, of course, comes along with the protocol, but apart from that, error estimation and correction, analysis, privacy amplification, these are all broad areas of research. In QKD, the requirement is that we first generate the pairs, we estimate the error, we do the error correction, we understand the leakages while communication, leakages in the transmitter, leakages in the receiver, leakages because of non-ideal components, leakages because of the electronics used, leakages also because of the quality of cryptographic algorithms, okay, and the security requirements. So all of that are analyzed and we come out with a formula, secure key formula. Before that, you have raw key. So you generate some raw keys and then you have error corrected keys. But secure key, whenever you're talking about a secure key, it's a huge area. So right now I would say that if you are generating a secure key at Alice and Bob, respecting the error margin and respecting the minimum threshold, data throughput threshold, and using very high quality and state-of-art technologies, that is a meaningful exercise. So right now when I'm talking, people are talking about hybrid QKD protocols, people are talking about methods to test and validate the quantumness of the QKD, the standardizing the different elements which goes into the QKD. Now, earlier I had mentioned about the security. I had told you that we use quantum principles, superposition, entanglement. So there are two types of QKD. One is prepare and measure, other is entanglement based. In the prepare, so we will talk about prepare and measure case in this presentation, but there is something also called entanglement based. Okay, and that is, of course, the security, it is non-local and it is based on the qualification factor, which is on the violating the classical inequality. So it is gives better security, I mean, reliable, but at the same time, it has very low throughput and very less, coverage area or range. But the prepare and measure, because of its nature of generation from the off-the-shelf components, it is much more prevalent. In fact, most of the quantum communication or QKD companies are based on prepare and measure. One such criteria is non-orthogonal. Now, this is a very important criteria because that actually gives you a, you will be able to, if you are using two non-orthogonal states, then one of the components will always be parallel and perpendicular to the other component. Now that helps you discriminate with certainty. Okay, because, okay, now to say that simply, if you have a rectilinear polarization, which is horizontal and vertical, and you have a diagonal polarization, which is a 45-degree and 135-degree. You use one measurement operator for rectilinear and another measurement operator for diagonal. Both these measurement operators, they don't commute. And since they do not commute, you cannot differentiate them with certainty, with highest precision. And so the maths, if you do the maths of these measurement operators, you will see it doesn't commute. Now, it is also very, you have to generate these states. In prepare and measure also, there are different ways, weak coherent state or a single photon state. So in the next slide, we'll talk about prepare and measure using single photon states. So this feature of provides quantum security to almost all, starting from BB84, B92, to other protocols, DPS, DQPS. So this factor, if you are interested in taking communication, you have to understand the preambles. So non-orthogonal states or a quantum state cannot be copied. These are few of them. So we will look into the B92 QKD. Now, Bennett proposed this in a paper, Quantum Cryptography Using Two Non-Orthogonal States. In BB84, we used 4, and in B92, we used 2. So I know that we are nearing lunch. Just bear with me for, I think, 2 or 3 slides, 2 slides more, that's all. So I'll request your attention for these two, because there are experimental results in the next 2 slides. So in B92 protocol, we have used a horizontal polarization and a 45-degree polarization. So you use one state from each of the mutually unbiased bases, rectilinear and diagonal. So use one element from horizontal and the other from the diagonal 45-degree. We designate them with ket 0, ket plus. So this is the protocol summary. We send randomly, we select. Of course, when Alice is selecting randomly, she has a table of what she is generating and what she's sending. Then Bob will measure the photon qubits randomly in one of these two bases. So when you are saying randomly, you need a random number generator at the Bob side to do a random measurement of these two operators. Bob keeps the qubits when he measures 1 and minus. You may be wondering, I'm sending 0 and plus, ket 0, ket plus, but Bob will keep the state when he gets ket 1 and ket minus. This will be revealed in the next slide, but please understand this analysis of why he chooses to keep these states. It is because if he gets 0, it can be a ket plus and a ket 0 state. And if he gets ket plus, it can be ket plus or a ket 0 state. This you can do a quick analysis when you are sending it to a 0 state. Sorry, so the mystery is revealed. So if you are sending a 0 state, then you can write them as in terms of diagonal states also, and you can write a diagonal state in terms of 0 plus 1 by root 2 or 0 minus 1 by root 2 for a ket minus state. So you do that exercise and you will understand why Bob is keeping and discarding the other states. So he keeps 1 and ket minus. And now this last step 4 is very important. This is the correlation which is used to generate the correlated binary sequence, which forms the raw key. So the schematic of the experiment is you have a single photon source, and we have used a weak coherent source, which means we are attenuating a laser to a level where it is less than 1 or about 1. So we keep attenuating it where the chance of having 1 photon is within 10 pulses. So average mean photon number is 0.1. Okay. So at that time, at mu equal to 0.1, you have the highest probability, 90% up probability of having a single photon in one of the 10 pulses. So then you have, so we generate the diagonal and the ket 0. There is a compute and communication engine. These two are at the moment in the table, they are a few centimeters apart, 30 centimeters something, but we will be taking them out and trying them for say about a distance of say 50 meters and taking it further. Then in the detector side, we have ket 1 and ket minus rest state he discards because of the earlier mentioned criteria. And in this manner, he creates a sequence of binary zeros and ones. He announces what he keeps. So Alice knows that if he's keeping a particular state, then according to her table, what that would be, and that helps creating a shared key. So this is the experimental setup of B92 protocol. So here the distance is about 34 centimeter. Of course, the first BB84 was also a few centimeters, no, before going to in kilometers. So this is where we start today. This side shows the source, the encoder, the random number generator. We have already generated RNG using quantum, so we are using that as a seed. Then you have a decoder. The box you can see houses detectors. It's a free space communication, but finally the result is taken through via fiber to these detectors. We are getting QBER. It's a very good number, 2% error rate, and that might change when we are adding more complexities to the system. For example, taking it out from the lab to the field. And at the moment, we are getting 10,000 bits per second on an average secure key rate. Now, you remember I told you about the zeros and ones. So ket plus, you can designate. This is very important. Okay. Ket plus, we designate as logic 0. And when Bob receives it, I told you, he will only keep the logic 1 state. And logic 1 state corresponds to logic 0. Ket 1 state and it corresponds to logic 0. So the thing is, when Alice is sending logic 0, Bob is indeed getting logic 0 and some QBER. Okay. This is the unwanted result, which has to be filtered and thrown out. So that also, this is also the reason why the key rate is less. So when logic 1 for Alice, ket H is logic 1. So whenever it is being sent, the existence or the presence of logic of ket minus tells that only H would have been sent, okay, which is logic 1. So my H, so the anti-diagonal ket minus corresponds to logic 1. So through this experimental test cases, it is evident that whatever Alice is sending, the same is received by Bob, whether it in the same logic 0, logic 1. Now logic 0 is encoded in ket plus in Alice and logic 0 is encoded in ket 1 for Bob. So I hope this is clear. Then we send some random numbers and we see equal distribution of these two logics. And this is an education module which which we are running in CDAC across 12 centers. And this is the AICTE syllabus, which I wanted to quickly show you. Uh, it's also the reason because you see materials, sensing, computing, and communication. But we were working only on communication, and through the photonics, we were working on computing. A lot of things in communication are dependent on materials, and a lot of applications, just like it was shown in computing, can also be shown in sensing. So though there are 4 technology areas, but all of them are very much connected. And that is the reason the course has been developed, keeping that in mind. And I hope you are all aware of this. And that brings me to the end. This is my team. So we have many people from MTechs in quantum technology, masters in physics, and VLSI and embedded and software in working in AI. So this is our team. And now you can. I'm open for further questions on this on QKD. I hope I've not put you to sleep.
Hello, ma'am. How large numbers can we decrypt using your systems?
So we are generating keys, symmetric keys. Now that keys will go as an input to the AES or a one-time password, encryption algorithms, and those algorithms will be encrypting the data, whatever is coming through. The data flow can be in gigabits. It doesn't matter. So now if you look at any of the cryptogram, what worries is the key. The key should be generated securely. The data size is still okay. I mean, if you want more data, you can keep on generating the seeds, storing them, and utilizing them. So there is no, I would say, there is no range of what data you would want. Right now, you're talking about gigabits, terabits. But if you want higher, then you have to use QKDs, which has a very high throughput in megabits per second. Ours, as you can see, it's on free space, and there are technological limitations of detectors. So based on that, our throughput cannot be more than kilobits per second. So, but it doesn't mean that if the seed is in kilobits, then the data which has to be encrypted and sent has to be in kilobits. It can be more. It can be in gigabits also.